Hello and welcome to the Google Tech Talk. Today it's my pleasure to announce and introduce Nikunj Oza from NASA Ames Lab, where he is the leader in the data sciences group, and he's going to talk about anomaly detection in aviation systems.
So yeah, I'll first give a little bit of a general overview of what sorts of problems are of interest to NASA, and then I'll go dive a little bit more into the problem of detecting anomalies in aircraft trajectories specifically, which is one recent focus area. I'll show just where data mining fits in, at least what we've thought of so far and what we've been implementing, what kind of data we get, algorithms, results, and then I'll give a brief overview of some other work that we're also doing in the data sciences group, and then also a little description of how you all can get involved in our efforts. So in general, NASA is aimed at problems in aeronautics, earth science, space science, and space exploration. And so the data science group looks at how data mining algorithms can be applied to these different areas. And so, for example, within aeronautics, a big focus of ours has been aviation safety. For example, identifying previously unknown anomalies that are of some operational significance that have a safety concern. We're also doing some other work in aeronautics, such as using machine learning for surrogate modeling. And also we are doing right now some text mining as well, where that's actually an effort that's been going for quite a while. Then as far as applications to earth science, one area is anomaly detection. There are numerous data sources, whether it's spaceborne, ground-based, airborne, where you expect there to be certain relationships between the measurements that are taken. And we spend some effort looking for anomalies in those relationships, because those may be indicative of some unusual phenomenon taking place. Also some filling in missing data. So this is the problem of when NASA develops new instruments that are deployed that typically collect data in a greater number of bands, of spectral bands than the older instruments. Then we use machine learning to actually kind of fill in what those measurements would have been for some of the earlier instruments, given that those earlier ones did not have the bands available. And of course, those are estimates, but we can at least use those to figure out some interesting phenomenon from the past. And then we've also done some work in space exploration, mostly in the area of systems health management, looking for anomalies in systems operations. Now, more specifically for anomaly detection within aviation, the current way that it is done, whether at the carrier level or at, say, within air traffic control, is that they use what are called exceedance-based methods. So there are certain anomalies that they know about that typically are conditions over 2 to 3 variables. You can think of them as maybe being rules. So I give one example here, that during landing, when the altitude reaches 1,000 feet, they would like that the aircraft is not traveling faster than 250 nautical miles per hour. If it is, that is sometimes referred to as a speed high exceedance. So for that particular flight, the system will essentially check a box saying that exceedance has been violated. They do typically also have a severity of exceedance that they indicate. And then, most flights will have at least a few exceedances, but they're, not such a big deal. Then they have a system, what's often called a morning report, where it'll show these exceedances for all the flights of the previous day. And so they'll look at it, they'll see, okay, most flights have some number of anomalies of some exceedances, but if they see a few flights that have many more exceedances than that, or a lot of really high severity exceedances, and they have not received a safety report from the pilot or some other member of the crew, then the carrier will go and talk to the crew and ask, okay, what happened with that? Now, this is great for identifying what they're looking for. So for example, for the speed high exceedance, if you want to find it, you have this rule, it'll find it. So it certainly has a low false positive rate because it tells you what you want, but it has a high false negative or misdetection rate, because almost by definition it cannot find what you don't tell it to look for. So we decided to come at it from the opposite perspective of saying, let's use data-driven methods to discover anomalies just by looking at the statistical properties of the data, finding which data points do not fit. You know, there's some, let's say, they're far away in some sense, or they are of low probability in some sense, where I need to, of course, define what some sense means. And I'll be getting into that a little bit later. The methods we've explored so far don't require background knowledge on the anomalies. So in some ways that's good. You're not entering with preconceived knowledge of how the system is operating. You're just telling the data to kind of speak for itself. And in this way, it's complementary to existing methods. I mean, it has a low false negative rate. We assume that data that appears normal through our methods probably represents normal operation, because overall, the aviation system we've seen is a very safe system. And we figured that the data points that are identified as anomalous, yeah, they may have some false positives because there may be data glitches, but we figured that new problems that people don't really know about are likely to be in that set of anomalies, the statistical anomalies. And the pipeline that we have used actually is what I described in the last bullet there, where we run these data-driven methods, identify some anomalies. Yes, some of them turn out to be false positive, but there are some useful insights that can be drawn from that, and they can be used to modify the exceedance-based methods. And in fact, we do have partnerships with some carriers where they have in fact told us that based on the insights of our algorithms, they have made modifications to their daily exceedance review. And so then that ends up being something operational then. So really, the key for us really is mining this heterogeneous data, because the national airspace and even the operation of a single aircraft is described by variables of many different modalities. So you have discrete variables. These may represent, say, like autopilot modes, switches that pilots may press during the operation of a flight. There's continuous data, things like altitude, airspeed, and others. Then there is what I call networks. Basically they're radar data. They represent trajectories that the aircraft travel in, and that's where you can have the possibility of interactions between aircraft. So there is, of course, the need to maintain certain separation between aircraft. So that's a key way in which the aircraft behavior ends up depending on the behavior of other aircraft. And then we also do have text. So there are the various carriers do have internal safety reporting systems, and NASA itself also runs what's called the Aviation Safety Reporting System, or ASRS. It's actually administered out of Ames. And after any commercial flight, any member of the crew or even a passenger, if he feels that there's something irregular of safety concern that took place on the flight, that person can actually submit a report. And then the report does go through some redaction process, and like some subset of the reports after being redacted are actually released to the public. And FAA also does keep track of these reports, find out about any new problems that seem to be popping up, and will work to investigate what changes can be made to the national airspace based on new problems that are reported. But so we would really like to utilize and analyze all of that data at once to find any new or emerging problems. So I'll go a little more into the specific problem of detecting anomalies in aircraft trajectories at this point. So there is a system run by FAA called the Performance Data Analysis and Reporting System, or PDARS. It gathers data from the US airspace, so the trajectory of every flight is recorded as part of this system. And it takes care of data quality issues. So in particular for PDARS, there are actually 3 different sources of trajectories that are used, and they are actually fused in order to create flight tracks that are more accurate than what each one would otherwise. That's where the merging process that I mentioned here takes place. And then as part of PDARS, some analysis and visualization is also done. And then this data is also made available to certain other key partners who also are interested in this area. There is the desire expressed at different levels of government to improve the analysis capabilities. There's the realization that there is this vast amount of data. we really need to do more to study that data in order to find new problems. And that's the upshot of what's being mentioned in in this case, GAO and the Office of the Inspector General. So that's part of what prompted our little effort, which I'll talk about at this point. So for us, we went into this really wanting to we thought that our data-driven methods could identify anomalies within radar track data, and so we ended up investigating that in 2 phases. So there was one phase that took place in 2012 to 2013, where we looked at 2 years worth of data involving LAX, and in that case, it was looking primarily at landings at LAX. As part of that effort, we ended up identifying 15 operationally significant anomalies where originally those were unknown, actually. So it was our algorithms that actually revealed these problems. Safety analysts said that these are of safety significance, and so some further investigation should be done. Then, as part of phase 2, we decided that we would look at air traffic that's of a very different type from LAX. And so that's where we looked at the Denver airport, because there you have much more foul weather than what you have in LA. So we thought maybe that there could be some new problems revealed there. And we also looked at the New York Metroplex. So this is primarily the JFK, LaGuardia, and Newark Airport. And then you sometimes also get traffic involving like Philadelphia and Teterboro involved in that. And that, of course, because you have these multiple airports with crossing traffic, that's much more complicated than what we've looked at so far. And so there's this kind of folklore also that says that if you can somehow deal with the New York Metroplex, you can deal with problems anywhere in the world. So that's why we thought, let's think big and try and tackle that. So this is just showing kind of the full process here of what goes on from data collection to any kind of analysis that we have. So at the FAA level, you have data that's collected at multiple levels. So there's, of course, at the airport level, and then TRACON and ART-CC describe broader levels that go beyond the airport that encompass multiple airports. And so you have data from each of those representing traffic, whether it's en route or during like takeoff or landing as well. Then all of these data sources are merged together and result in the PDARS data that I described before. One thing that we did not have within the phase 1 in LAX, but we do have in the phase 2 at Denver and the New York Metroplex, is this calculating of the flight separation. So in the LA effort, we only look for anomalies in the shapes of the trajectories themselves, without necessarily looking at whether there were cases where aircraft were unusually close together. We ended up adding that step for the second phase in looking at Denver and the New York Metroplex. Then this is kind of where we came in, the NASA portion, where we took this data and we actually separated the data by runway and by month. So, because of course different runways, depending on which runway is chosen, you're going to have different trajectories, and so that's why we wanted to look at each of those separately. And then we separated by month, looking for anomalies like separately for each month, just to account for any kind of seasonal characteristics that may be present. Then the main algorithm we ran is the multiple kernel anomaly detection, or MCAD algorithm that we developed. I'll be describing that a little bit more later, but essentially, it takes the trajectories that we enter and it rank orders them from most anomalous to least anomalous. And so once we get that, then we do a review with subject matter experts. First, our partners at ATAC, which is a company near the San Jose airport that we're working with, which has access to PDARS data. So they have people who are like former air traffic controllers and generally are experts in this area. And they review these flights going through, more or less in order from looking at the anomalous flights and seeing, is there some kind of a safety concern there? And we have also, once they vet the flights, we have shown them to air traffic controllers who have generously volunteered their time to explain what's going on. And in cases where in some cases we have had voice recordings available, so then we've been able to understand what's going on. But if we have not had such access, these controllers have been able to provide fairly educated guesses about what may have been going wrong and why the anomalies that we found were significant or were not. So this is just kind of another diagram showing what we're dealing with here. So we, starting with the TRACON or indeed any other data sources that may have been merged with that, we'll identify a set of airport arrivals. And typically, for whether it's LA, Denver, or New York Metroplex, we've had anywhere from about 100,000 to nearly 400,000 flights that we've ended up identifying and then working with. But then we do end up for, so there's the mining system where I mentioned that we separate by runway and by month. We do also have a prototype system that is operating in more of this morning report style that I mentioned, where it's looking at flights of a given day, giving an indication of how anomalous it is, and then providing a report the next day. That's more or less what's described here, where we also do, like after first doing some testing, then we'll incorporate those into training, and that's what's depicted here, where we then end up taking some training flights, separating them by runway, and running our MCAT algorithm, getting a model, identifying anomalies, and then doing whatever follow-up needs to be done, whether subject matter expert review, for example. So the multiple kernel anomaly detection algorithm, it's basically a one-class support vector machine, which many of you may be familiar with. The upshot of it, you can say, is that we assume that it's kind of, I think I described this a bit earlier, but the idea is that a flight, we consider it normal if it's similar to most other flights, whereas we figure a flight is probably abnormal if it's different from most other flights. But then the question is, how do you measure similarity or difference in this case? And so the way we measure it is really through this, what's shown here. So I haven't gone into the full, the setup of the primal of the one-class SVM. I'm showing here the dual form because that's at least somewhat revealing, or as revealing as equations can be right after lunchtime. But what this one shows is the vanilla one-class support vector machine will have one kernel function here, where you can see here I've shown a kernel function applied to two data points, xi and xj. In our case, those will be two trajectories. So if two trajectories are very similar, let's suppose they're one on top of the other, they're the same flight, then the kernel is going to return, or should return, a value of 1 in that case to reflect maximum similarity. Whereas if two trajectories are very different, they should return a much lower value, one that doesn't disappear hopefully, but it should return a value, say, close to 0. And using this machinery, if you have a set of flights that you're checking, then all the distance from or similarity between all pairs of flights is calculated. And so using that, you can determine for any flight how similar it is to most other flights to answer the question of whether it's normal or anomalous. But now that works fine if you have one modality of data, but I described the problems we had earlier of having data of many different modalities. So I described for a single aircraft, you may have, say, discretes, continuous. You may have even safety reports that are associated with that flight. How do you put all those on? You can't imagine putting those on the same coordinate system and then and doing, let's say, clustering and checking for anomalies. So what we do is have a separate kernel function for each modality, and actually that's kind of what I describe here. So for the single flights, we actually ran this same algorithm, but with a separate kernel for discrete, separate one for continuous, separate one for text. At one point, we even tested incorporating weather data into this. But now for this trajectory problem, we use the same algorithm, but we have different kernels for latitude, longitude, altitude, and distance to the nearest aircraft. And the good thing here is that we can actually use different kernels that are appropriate depending on the modality here. So for latitude and longitude, we just use a cosine similarity kernel, since that ends up taking into account the locations and directions, therefore, of the trajectories that we end up getting. And then altitude, of course, is on a very different, it's on a very different scale here. But we still ended up using cosine similarity for that, but of course normalized the data very differently. For the distance to the nearest aircraft, we ended up just using this radial basis function kernel that's shown here. And then for the case of where we were looking at individual aircraft, we used, of course, fairly different kernels for discrete, continuous, and text. But the key point is that then rather than working in your original data space, you're mapping all the different data with all their different modalities into this similarity space, where for all modalities, you're just getting these values ranging from 0 to 1. And then with the multiple kernel method, you can just measure the similarity between two data points by taking their averages over all these different modalities. So for two trajectories, that's exactly what we do. We take these measures of similarity over latitude, longitude, altitude, and distance to nearest aircraft, and just take a convex combination, which is depicted here. We so far have only explored having equal weights for all the kernels. You could, of course, decide to explore giving different weights to different kernels if you like. And otherwise, though, you still have the same machinery as with a one-class support vector machine, where you end up with, in this case, which actually end up, I guess I can probably show it here. The data points that end up having these alphas being positive are what are called the support vectors. So some of the benefit you get, especially when running the support vector machine in a testing mode, is that you don't have to have all of your training data. Essentially, the algorithm figures out what are called the support vectors, which are the key data points that you need to determine the separator between normal and anomalous data points. And so that only those data points end up being used here. And instead of a single kernel, you can still use multiple kernels. So like when say a new flight comes in, it's compared against all of your training flights using this kernel. It could be a single kernel, or in this case, it's a combination of multiple kernels. And then that is used to assess if the data point is an outlier or is normal relative to the training data that you already have. And we get also an indication based on how strongly negative or positive the value, the decision value that's returned, you get an indication of how strongly normal or anomalous it is. And so that's where we're able to get that kind of rank ordering that I described, where then the subject matter expert is able to go through the flights in order. So I'll describe some results that we got. So one example that we found is the case of a loss of separation, as it's called. So in this case, the aircraft that ended up being identified as anomalous is the one that's indicated here in orange, and it ended up getting relatively close to another aircraft, not only in the lat long space, but also in terms of its in terms of altitude separation here. And this particular trajectory ended up showing up as anomalous because this orange aircraft was on descent, and then it suddenly stopped and actually climbed a little bit in order to avoid getting too close to this other aircraft, and then continued on its descent after that. So especially the shape of the trajectory, ended up being key. I think, the distance to the nearest aircraft also ended up being a factor in this particular case. So one thing that we were told by our domain experts is that this was in an airspace where there may have been controllers handing off the aircraft, so meaning at maybe one controller was managing it and then he was supposed to hand off to another controller because you reached, say, a boundary in the airspace. So they hypothesized that this particular area where this happened may be a so-called hotspot where there are more likely to be problems because of handoffs to other controllers. So this is one where there was a go-around that happened due to high speed. So in this particular case, the trajectory that the aircraft ended up following was that it came down this way. He was going too fast, in this case over 250 knots at about 2,500 feet while landing. He was supposed to land on this runway here, but he kind of overshot this and then was unable to line up in time to be able to land here. So then he decided to, or it was decided that, that he should do a go-around. Overshot the runway again a little bit, but not by as much of a margin. So this time he was able to, it was able to land. So this ended up showing up as an anomalous purely because of the unusual shape of the trajectory. You don't get this kind of thing happening very often. So, that's where this ended up being identified. Another one that we had was what we call a recurring high-speed vertical descent. So this was in case it was a cargo aircraft that regularly lands, in this case at JFK, sometime from 11 p.m. to 1 a.m. And there's kind of this agreement that this particular aircraft, being a cargo aircraft and being at night, is allowed to take some creative approaches to landing so that it can get closer to the cargo terminal, so its cargo facility. So there is kind of a standard landing it's supposed to go on, but the thought is this is middle of the night, there are no passengers who would get frightened. And so, they can allow these somewhat creative maneuvers to take place. And you can see here in the diagram the kind of the range of different maneuvers that are taken. It's, quite amusing, unless you have to fly on it, I guess. But so in this case, I mean, there's, not really a safety issue here, but the safety analyst did point out that since this is, not really following the standard operating procedure, if a new controller comes online, that person may not be used to this, may cause some difficulties, or, may raise alarms where it's not really needed. There was the thought that then, maybe procedures like this should be codified so that any new controllers that come online know that it's okay to do this. And so in that way, the anomalies that we find can be used to actually add to standard operating procedure. So another one, this is just, I guess a somewhat more, I shouldn't say more routine case, but this happens every once in a while. I mean, a key job that controllers have is to ensure the spacing between aircraft that are going to land. So they have a system where they identify slots where aircraft can be plugged in order to then land. And this was a case where it looked like there could have been a potential tie situation where two aircraft are trying to land at the same runway, and there was there would have been reduced separation, and so that in this case, this particular aircraft was told to go around. And I think this is one where there's an animation here. Yeah, this is just showing the aircraft here. Not quite sure about the reason for this little here where it gets off of its approach here, but then you can see that the red aircraft gets relatively close to that other one, and so then that's where it's told, okay, you probably better go around. And then, yeah, eventually, though, he does go, all the way around here, and then finally does end up, landing on this particular runway. So I should say this is part of the procedure also that our collaborators at ATAC follow. So when we identify a particular anomaly, they'll typically pool up traffic starting maybe half an hour before, just to see what the whole traffic situation is, see if there are any funny things that are brewing up in advance of the anomaly that we identify, and then they'll make animations of this sort to show, let's say, not only this particular anomaly, but maybe even other issues that pop up before that. And for our work in the LA area, we were not able to get access to voice recordings because there is a publicly available archive of voice recordings, but that only goes back like 45 days. And we ended up looking at data that was about a year back in time. So that's where we relied a lot on the educated guesses of the controllers to tell us what may have been happening. But with our work with Denver and the New York area, we've been able to get access to voice recordings. So sometimes they're not present, but once in a while we're able to get explanations of anomalies using the voice recordings. So this is another particular anomaly, what is termed, I guess, an aggressive runway change. So this was the case of the anomalous flight, again, is in orange. And this is one where aircraft was lining up for approach, but then he was going faster than the aircraft in front here, and so there was what they call a potential overtake situation. And so for that reason, this aircraft was told at least not to land here on this particular runway. The decision ended up being made to instead land on this different runway here, but the turn that he ended up taking was kind of relatively sharp. And as you probably know, I always hate diagramming airplanes with my hands, but when an aircraft is say turning to the right, it has to bank. So you'll end up turning like this, and the same thing happens with this aircraft. There was here, you can see this aircraft in blue that was getting ready to land on a parallel runway as this particular orange aircraft was banking to the right. And that yields what is called a belly up situation. So essentially this orange aircraft was not able to see this aircraft in blue while it was landing. And that's because it's a quote belly up situation. The aircraft isn't able to see anything that's at its belly, so to speak, if you anthropomorphize the plane. And that's a situation they would prefer not to have. As far as the safety impact of these data mining algorithms, what our collaborators at ATAC and the controllers have told us is that they see these anomaly detection methods, whether it's MCAT or other methods that could be used, can be good to automatically identify certain safety risks and also provide kind of like morning report style feedback and really identify new problems that they're not set up to look for given the current exceedance-based system. I mentioned the problem of being able to highlight certain problem areas or hotspots. If anomalies seem to show up in certain areas, then that may be indicative of, say, issues related to like one controller handing off to another. Also, there's, I mentioned about the idea of the recurring non-standard operating procedure maneuvers, things that these behaviors that just sort of emerge where there's really not a safety issue, but these have not really been codified, and our algorithms can help reveal them and provide some sort of impetus to actually codify these different ways of operating. We can also use this to help assess whether new procedures or tools are improving safety, and that's something we're actually getting into now, is looking at operations, say, at a given airport before and after some kind of procedure change to see what the overall impact on safety is as a result of that, see what kind of anomalies like maybe were there before that are not present now and the other way around. And then it can also help to identify key training examples, not training examples in the way that we machine learning types would think of it, but examples for training of controllers in this case is what is meant. So identifying certain kind of borderline safety situations that could be good to train controllers on. As far as the work that we're planning, right now, when we run our anomaly detection algorithms, domain experts give some kind of feedback on whether those anomalies are operationally significant or not. They may give us an indication of why. That is not fed back into the algorithm in any way. Like the one class SVM runs, but that's it. There isn't some kind of feedback that goes into that. We are looking at augmenting MCAD with active learning methods that can be used to provide this kind of feedback. Of course, the difficulty that we have is that we're looking at not only the notion of a flight being anomalous, but then trying to identify parts of that flight that are anomalous, and oftentimes the feedback is in that form, that here's a specific portion of the flight, like over these variables or over these particular ranges of time that are anomalous. How can that be incorporated into an algorithm that's looking at data at the flight level, really? But that's something that we are working on. I mentioned this prototype daily reporting system that we have set up at ATAC. It still needs to go through a proper evaluation over many days, really seeing what kind of false positive rate we have, what kind of new problems are being revealed. We would also like to develop some sort of way as part of our system to automatically classify the known identified events. So maybe even using the exceedance-based system to tag parts of the flights that we know are anomalous, or maybe even based on feedback that controllers and other experts have given. There's also the desire to automatically link certain visualization tools. So, I mentioned about how we use voice, weather. I showed some of these animations, but those are all operated separately. So over at ATAG, there are different systems that are used for all of these. We would, of course, like to have a single integrated system that's able to pop up an anomaly, pop up the voice that's associated with it, pop up, like bring up the weather, automatically bring up the traffic. I described about how our domain experts bring up the previous half hour or so of traffic to see what's been brewing up in advance. Bringing that up automatically would be good. I guess I described also the bottom problem there of studying the airspace before and after a procedure change. As far as other work that we do, we have done anomaly detection in flight recorded data by itself and also jointly with safety reports. So there's one carrier with whom we've partnered where they have allowed us to actually tie the flight recorded data with safety reports. And so we actually use MCAD to mine those all at the same time and look for anomalies across that. So that's certainly something that we'd like to do. There's the text mining on the aviation safety report. So I described that aviation safety reporting system. That only has reports by itself, not tied to any flight recorded data, but certainly more mining of that kind of data would be helpful. We also really want to identify precursors to anomalies in the sense most of what I've described here is really trying to identify a single anomaly that's taken place. What we're really interested in is what it was that happened before that could have possibly led to this brewing up. So why did the one aircraft nearly overtake the other? Was he busy doing something else? Was he looking at his iPad? Was he arguing with his co-pilot? Some of that we may never find out because we don't collect data, for example, from within the cockpit necessarily. But we may be able to monitor, say, the switches that are being pressed. We may be able to figure out that, okay, there's, let's say, a rapid sequence of mode changes in the autopilot that may be indicative of what's called mode confusion, where that's the case where the crew doesn't really understand what mode the aircraft is in and is trying to figure that out. And of course, that takes brain cycles, which may need to be used for something else. So that's certainly something that we'd like to do. We've done a little bit of that kind of thing so far, but certainly more of that is needed. We'd really like to go ultimately towards identifying a sequence of steps that went from, say, a state that's perfectly normal but just happens to be more likely to lead to some unsavory state than other ones, and then see what is kind of brewing up until some operationally significant anomaly actually takes place. We do have it's a facility, it's called the NASA Earth Exchange, so that actually ties in NASA's supercomputing assets and massive data storage together with I guess you can say a kind of a social networking / collaborative system that allows, in this case, Earth scientists to run different analysis algorithms on massive data sets and document them for reproducibility and for sharing with collaborators. And we had a project funded competitively by NASA to implement our data mining algorithms for use within the NASA Earth Exchange. Here I described just some of the partners that we've had especially on the aviation safety side in our work. So as far as how many of you can get involved, we have a system called DashLink. Blue may not be the best font here, but this is an HTTPS dashlink.ndc.nasa.gov. It's this it's a collaborative website. It's for people who are interested in data mining and systems health management primarily. Any of you can join. You would need a civil servant, a NASA civil servant, to approve you. I would be happy to do that. Please do mention this talk as part of that. And this is a place where you can set up profiles of your own describing your research. You can set up project pages. You can set up data sets that you are allowed to release to the public, and you make them available for others to work with. We put some of the data sets that we're allowed to release on there, and then our data mining algorithms, we open source them and make them available on Dashlink. So the MCAT algorithm I described is available up there for people to use, and we in fact have had carriers that have gone to this, downloaded the algorithms, and tried them out on their own. And we'll help answer questions within reason. So this is our team at NASA. You can see right now we're at 10 people, split about evenly between researchers and like programmers and support type. And we're, of course, most of the work that I described here is funded by our Aeronautics Research Mission Directorate, but we do have certain also externally funded projects. The NASA Science Mission Directorate also provides funding, but they do it entirely on a competitive basis, whether the people proposing to do the work are from NASA or not. So then, that's another way. The NASA Engineering and Safety Center, you can think of it as kind of an internal consulting arm, where if a problem comes up where they need some kind of quick turnaround solution, then they often go to the NASA Engineering and Safety Center, and we have gotten involved where it was felt that data mining could be of help. So just I put my email address up there in case you want to hound me about anything I've mentioned here. And this is just some reading in case you're interested. So this first paper here describes our work on anomaly detection for the LAX area, describing many more anomalies than what I could have here. The second paper describes our work for the Denver and New York Metroplex. This third paper here goes into the multiple kernel anomaly detection algorithm, and it gives a few results involving individual aircraft, the what's called Flight Operations Quality Assurance, or FOQA data. And then this last one was one I didn't end up getting into this work, but we've developed an algorithm that's primarily based on inverse reinforcement learning, but has a standard reinforcement learning component to it as well, that we used for the problem of identifying precursors to particular anomalies. So what this paper describes is the case where you have identified, say, I think I described earlier the high-speed exceedance, so where during landing you're going too fast for the particular altitude. So with this algorithm, we were able to set that up as the effect, and then our algorithm is able to identify what seem to be the precursors to that. So we end up kind of identifying, I guess, what you can consider kind of an envelope of energy state, where you can say that even earlier in the flight, if you are traveling faster than a certain speed, you're probably kind of beyond some point of no return, so to speak, at least given the data that we have. So that's just a rather preliminary test, but we certainly do plan to use this to identify precursors to other particular problems that, say, a carrier or FAA or others identify as a problem they're particularly interested in, for which they would really like to know what the precursors are. So that, I believe, is the extent of what I had planned to say. I guess I can put that last slide up and take any questions.
Thank you, Dr. Oza. For the benefit of those who are remote, if you are going to ask a question, please use this microphone. So,
can this detection be used to detect the drones when they are going in the wrong directions, things like that? Because I'm imagining in the future when drones are we have more and more drones, there will be accidents.
Yeah, I certainly think so. I mean, if you would have to have enough traffic of drones to where something like MCAD can get a sense of what would represent normal behavior of the drones, so that you can say that, let's say, the drone that's going in the wrong direction should be quite atypical given the data that you have. But yeah, at least I think actually the algorithm as we have it, with the latitude, longitude, altitude, and maybe distance to nearest aircraft could be relevant, but yeah, I think so. Oh, I should add, though, that we, at least so far, have not set it up for real-time monitoring. So yeah, this is something that it's really set up right now to only operate for the case where, let's say, flights have already been completed, and then after the fact you are looking for anomalies. So Yeah, for the real-time case, I think that that's something that we're thinking of now, more than before. I think given the way the NASA's projects are evolving, I think we're going to be looking at the real-time case a little bit more in the future.
So I'm curious, for an incident where an airplane ends up in the Hudson because some birds affected the engine, do you filter that out, or do you actually include that in as a way to detect similar anomalies?
So we don't necessarily eliminate particular flights right now. I mean, I know that the data that we get does not include, say, like military flights or other ones where they would rather that we not, look into them any further. But I think that the inclusion of flights that are anomalous shouldn't really affect us too much. I guess if a certain flight occurs too many times, it may start to show up as normal given our algorithm. So that may be of concern. But something like this, it should be rare enough that we'd be able to find it.
Is it okay to ask about this multi-kernel SVM thing?
Oh, sure, yeah.
Yeah, so the convex combination of kernels is a kernel itself, isn't it?
Oh, yes.
Yeah, so for the sake of understanding, would it be right to say that you're looking for a kernel, for a kernel of this form, which actually maximizes the margin, like in this algorithm or something like, could you please, if possible, decouple the kernel you're looking for from the algorithm itself? Like, is it possible, like, to understand the properties of the kernel without knowing the SVM itself?
Oh yeah. Because in fact, yeah. We are able to develop the kernels the way they normally are developed, just making sure they follow things like the Mercer's conditions. In fact, like for us, one of the good properties of this is that we are able to share the kernels with domain experts, and they're actually able to understand that they make sense. So for example, for the case of the individual flights, where we have the discrete and continuous, just for example, for the discretes, two flights are going to, or each flight is just going to have a sequence of switches, essentially. And so the kernel we use there actually is the normalized longest common subsequence. So in that case, like two flights, if let's say they're exactly the same, their common subsequence is going to be the full flight, right? So that would then end up normalizing to a length of 1. Whereas if two flights are very different, there's going to be only a very small part that's common to them. And so the length of that would normalize to something that's relatively close to 0. And so that's something where we were able to explain to domain experts, and they were able to say that, okay, yeah, this makes sense. We did end up adjusting the values of some of the switches because some of them were deemed to not be as relevant. But then we were just able to then include that here as part of the algorithm. And then when we transitioned over to the trajectory domain, we kept the algorithm exactly the same, except just swapped out kernels.
May I have a follow-up question? Is there any problems you know of with this approach, like maybe algorithm tending to prefer some kernels over the others, or something like that?
Yeah, actually, yeah. When it's certainly that can be an issue. So, one issue that we haven't dealt with at all really is the case of where you just have these separate kernels and what kind of weight are you giving to them. So, should the text kernel, for example, have the same weight as the discrete and the continuous? I'm not really sure. But then, I guess another issue also that we kind of have noticed is that for the continuous kernel, the way we actually do it is that we take all of the variables, however many they were. I don't think we've ever used more than 20 continuous variables at once. But what we actually do is discretize each of them using the symbolic aggregate approximation, the Sachs approximation that Eamon Keogh and his colleagues developed. It's a way of just discretizing all of the different variables. And then we actually put all of those into a single discrete sequence corresponding to the times when each variable has a change from one discrete bin to another. So we note the times at which each variable has a change in the discretized version. note the time at which it happened, and we put those changes in order into a single sequence. Now, the problem then with that is that you're taking so many of these continuous variables, putting them into a single sequence that has a weight of like, 1/3 or a quarter. Now, there may be significant changes in one or two of the variables that are kind of getting washed out in the process of doing this combination with so many other variables. That's admittedly something we still have to resolve. Is that along the lines of what you're mentioning? I'm sorry if I'm...
Yeah. And may I ask the last question? Yeah, sorry. So I've heard that sometimes when you try to discover anomalies, you have a lot of normal cases and only a few anomalies, and that throws the algorithm off. So do you have such problems? And if you do, then how do you deal with them?
So we haven't had a huge problem with them so far. I guess kind of maybe the biggest problem we've had is that for the case of, say, the flight recorded data, there tend to be a fair number of go-arounds. So we tend to get a large number of them. And they are of varying interest. Some of them are just routine ones where they say, okay, it's not really a big deal. Some of them are of concern not so much for the go-around itself, but maybe what prompted the go-around. So I showed examples of things like the potential overtake situation. So the problem is not so much the go-around, but the overtake. So, but sometimes go-arounds seem to happen for certain whatever other reason, and there doesn't seem to be a concrete precursor to that, and it's not that big a deal. That overall is probably the biggest issue we faced. Also with the trajectory anomalies, we haven't really had the case where a flight was identified as, let's say, abnormal that turned out to be like perfectly normal. But sometimes those are not of safety concerns because let's say it's maybe an unusual trajectory, but it happens at night. So there aren't too many other aircraft around, so it's not such a big deal. Or I described the problem of the cargo aircraft where like passenger comfort is not really an issue. So in that case, trajectory anomalies are okay. We have had cases actually though with unusual trajectories where it turned out that instead of a commercial aircraft, it was a regional jet. And regional jets being smaller are much more maneuverable. So I guess that's one case where something that's normal pops up as an anomaly for us. We've had a few of those. But yeah, overall hasn't been a big problem.
So most of the examples that you showed were of anomalies that were sort of detected in real time by the controllers or were of no concern to the controllers. Did you find any that were not detected and perhaps should have been?
So actually, so actually for the ones that I showed, they were ones that at least, they were ones where the safety analysts did say that it should go through some further review where they had not originally planned to. So it was, as you said, I mean, they were likely things where during the operation, yes, controller realized, okay, something was happening and let's say a go-around should be issued. But they didn't didn't decide to put it through some kind of further safety review. And it was after our algorithm was run that they decided that it should go through some further review at least.
Okay, thank you very much, Dr. Oza, and thank you.